Okay, related to the first order, zero order, or some other order of the reaction. Let's see some points which are needed. Point number 1. For calculating the related to the half-life period, suppose if the some amount of reactant is given, you have to calculate the left amount after certain half-life period. Then for that we have a formula. That formula is AT is equal to A0 upon 2 raised to n. AT is equal to A0 upon 2 raised to n, where n stand for n is, it's a not order of reaction, instead it's a number of half-life period. So in this formula, the n stand for number of half-life period. It doesn't represent the order of reaction. A0 upon 2 raised to n. For example, suppose I have a question is asked like calculate the order. The question is like if 80 grams of reactant was taken in the beginning, then how much amount of reactant will be left after 4 half-life period? So initial amount which was taken is 80 molar reactant was taken, and I want the concentration of reactant after 4 half-life. So here I can say n is equal to 4. Initial amount was, that is A naught, as I said it is 80 molar, and we have to calculate 80. So simply I will use this formula. So 80 will be equal to, it is going to be A0 upon 2 raised to n. 2 raised to n, that is 80 upon 2 raised to 4. 2 raised to 4 means I can say 80 upon 2 raised to 16. 2 raised to 4 is, that means 5 molar. So after 4 half-life period, 80 molar of reactant will get reduced to 5 molar. Either use this formula, or we can solve the same numerical without formula also. Suppose in the beginning I was having 80 molar of reactant. Here we are considering 4 half-life. So I can say after first half-life, the reactant left will be 40 molar. After next half-life, it will be left only 20 molar. And if I am using the next half-life, that is after third half-life, it will again reduces to half, because we are talking about the first order reaction. So after next half-life, it will again reduces to half, that means it will become 5 molar. So how many half-life is taken then? 1, 2, 3 and 4. So either use this method, or directly by using this formula we can determine the amount of reactant left after some particular time. Then the second note, or the second important point, whatever the radioactive disintegration we have, all radioactive decay processes are considered as a first order reaction. That means the radioactive decay depends upon the rate of depends on the concentration of the only one reactant, that is that particular radioactive element. Then next, T half of whatever the radioactive decay we have, like if the radium is there and if the some alpha beta particle is emitting from it, then that emission is going to be the first order reaction. So after this, now the third is, the next important point is T half is directly proportional to A0 raised to 1 minus n. T half, that is half-life period, is directly proportional to A0 raised to 1 minus n. So depending on which order of reaction we are having, we can write the relationship between the half-life period and the initial concentration of reactant. We just did the half-life period for the two reactions, that is a zero order reaction and first order reaction. In zero order reaction, we come to know that half-life period is directly proportional to initial concentration, while in case of first order reaction we come to know that it is inverse, it was independent of concentration of reactant. So this also gives the same relation. So here if I am considering as a zero order reaction. For zero order reaction, T half. Zero order means 1 minus 0, so I will have T half is directly proportional to initial concentration. If I'm considering second or first order reaction, first order where n will be equal to 1, so I can say T half is directly proportional to A0 raised to 1 minus 1, that is 0. That is, T half does not depends on initial concentration of reactant, I can say. If I'm writing for second order reaction, then I can say T half is directly proportional to A0 1 minus n. N stand for n. Again, n is here order of reaction, that is n is equal to 2 here. So 1 minus 2, that is A0 raised to minus 1, which can also be written as T half 1 upon A naught. That means inversely proportional to initial concentration. Now in this case, n stand for the number of half-life period, while here the n stand for order of reaction. In a chapter only, this is the formula where n stand for the number of half-life period. Otherwise, in all the cases, n stand for the number of half-life period. So the next point. Unit of K. We already had determined the unit of K. We are having a 2 units. Both are nothing but same, only the way of writing is different. The first one was molar raised to 1 minus n per time, and the second one was mole per liter per time. Mole raised to 1 minus n, liter raised to n minus 1 per time. So where again in the unit we have n, that is the order of reaction. So depending on order of reaction, the unit of K keeps on changing. So let's see the unit of order, unit of K. So here we have order, unit of K. We have 2 units for K, m raised to 1 minus n, and then per time. And the another one is mole raised to 1 minus n, liter raised to n minus 1 per time. Here while writing the unit, I am considering time in seconds, but depending on if it is in minute, you have to write in minute. If it is in seconds, then you have to write second, and if it is in hours, then you have to write in hours. So first order, for zero order reaction, for zero order means n will be equal to 0. Then we will have m raised to 1 minus 0, that is m only, and per time. And here I can say mole raised to 1 minus n, that is mole. Liter raised to n minus 1, 0 minus 1, that is minus 1, and per time. You can say this is nothing but, okay, so here we are considering time in seconds. So it's a S, and this is also in second. You can see that here the unit is nothing but the unit of rate constant for the zero order reaction is like the unit of the rate of reaction. And we have also the same thing, now means for the zero order reaction we have rate is equal to K. So if the rate is equal to K, that is the unit is also going to be same. If I am considering a first order reaction in this case, first order reaction where n is equal to 1, so there is a no m, it is only per second. If it is in minute, then it is per minute, hours, then per hour. Same thing here, 1 minus 1 or n minus 1, that is, it is again 0, so per second. If I am writing for second order reaction, n is equal to 2, then it will become 1 minus 2, that is minus 1 m raised to minus 1 per time. and similarly here mole raised to 1 minus n, that is 1 minus 2 per time per molar, liter raised to 2 minus 1 is 1, and per time, that is per second. And for third order, n we have 3, so it will become m raised to minus per second, and this will be mole raised to minus 2, liter raised to 2, and then per second. So we are having these as the unit of a K. So here I can say on the basis what will be the unit of K, it is totally decided by the order of reaction, or in other word I can say the order with the help of the unit of K I can decide the order of reaction. Suppose if there is some question and in that question we require order of reaction, but the order is not given directly, so better to know the order of reaction. They may give the unit the value of K, and if the K value is given, that means the unit will also there. For example, suppose there is some reaction for K in which K is equal to given as 4.2 into 10 raised to minus 3, m raised to minus 3, and per second. Now I wanted to know the order of reaction, so simply I will say m raised to minus 3. M raised to minus 3, think about what will be the value of n, so that you will get m raised to minus 3. Then I will say the value of n should be 4, means the reaction is going to be fourth order reaction. So with the help of the unit of K, we can decide the order of reaction. Means it also helps us to know the order of reaction.